Today, modern AI system design generation can synthesize a mechanical architecture of this complexity in a matter of minutes. The resulting output appears remarkably robust, providing a defined payload architecture, specified materials like carbon fiber, and detailed kinematics for the two-axis gimbal. This wireframe reveals extensive underlying data, a comprehensive bill of materials, interface records, and specific failure mode and effects analysis findings. But this detail often hides severe structural gaps. Verified data frequently reveals unresolved component references, absent physical transforms, and failed assembly validations. AI synthesis functions as a sophisticated proposal, lacking the strict governance and mathematical validation required for a production-ready engineering model. To translate this proposal into an actionable model, Genesis Design Studio uses a strict model-based systems engineering workflow. Rather than allowing an AI to silently hallucinate parameters to patch over missing data, this workflow acts as a mandatory filtration layer. The first objective is to deliberately expose the breakages in the data structure, giving human engineers direct visibility into exactly what is missing. The second objective is to take abstract system requirements and map them forcefully onto the physical architecture. True engineering continuity requires a traceable baseline, achieved by rapidly stripping away the visual polish of an AI concept and organizing the raw data into a strictly governed hierarchical structure. The specific failure modes generated for the gimbal assembly illustrate the danger of these data gaps. The AI correctly flagged several high-priority physical threats, including power connector fretting corrosion. In a raw output, this severe risk record is often completely orphaned, pointing to a component ID that does not exist in the final build list. If a tool silently infers a connection or hides this unresolved ID to keep the dashboard clean, that unmitigated risk passes straight through to manufacturing. Explicit tracking of missing data is vital for maintaining model integrity and preventing hidden failures. Genesis intercepts these errors by routing every generated artifact through strict MBSE flow requirements. Flow Rule 008 governs data quality. Conflicting parameter values are mechanically intercepted and isolated into a dedicated data quality register. Simultaneously, Flow Rule 009 establishes a missing data register. Any necessary model artifact that lacks explicit parameters, like these ghost components, is captured here for human review. These registers drag unresolved references to the surface, demanding direct human accountability before the system can advance. Exposing structural gaps ensures engineering accuracy, whereas hidden flaws reduce an automated tool to a superficial demo generator. We can apply the same rigor to the physical structure of the quadcopter. A physical bill of materials lists existing parts, but lacks the logic defining how those components operate together or fail under stress. Risk is relative to function. A component becomes a liability only when viewed against the specific requirement it is engineered to satisfy. Genesis solves this through functional allocation. This motor schematic shows a link passing from an alignment requirement through the component to the functional objective to provide lift. The linkage extends downward, connecting this objective directly to the threat of a motor winding short circuit. Customer requirements are converted from static pros into atomic, testable objects tightly bound to the physical parts. Beyond the parts themselves, the model must map the boundaries of interaction. The physical interfaces between components are where most system failures originate. Modeling requires explicitly mapping the load types and magnitudes crossing these boundaries. This joint cross-section tracks distinct mechanical load vectors and thermal transfer paths interacting under operational stress. Encoder signal noise and fluid seal paths are also recorded as explicit interfaces, carrying defined target elements and acceptance criteria. Tracking these precise interactions feeds real-world operational stresses back into the design loop. Explicit interface mapping and functional allocation ensure the FMEA covers actionable physical mechanisms rather than guesswork. The ultimate value of this data architecture appears during assembly validation. An AI output might clear 10 out of 12 basic digital intersection checks, while a critical physics check, like the center of gravity balance, fails outright. In a traditional environment, a failed physics rule often disappears into a static status report. Genesis captures that failed rule and automatically converts it into persistent verification evidence within the model. Because the architecture is mapped, the failure status traces backward up the chain, triggering alerts on the specific component and the overarching requirement, automatically generating a corrective action candidate. This forces the engineering team to either schedule specific physical testing or execute a design mutation to fix the offset. The failure is permanently locked into the system, definitively ensuring that flawed geometry cannot proceed to the manufacturing floor. Routing validation failures backward transforms static analysis into an active reliability loop. Finalizing the design requires addressing a common industry misconception regarding system modeling code. Generating a clean SysML version 2 text file is an essential first step, but raw text is not a substitute for a structured, native Cameo project. Raw code lacks the diagram layouts, missing metadata annotations, and tool stereotypes that professional environments require. The Genesis validated mapping pipeline handles this translation to ensure absolute semantic preservation across the model. Raw AI design synthesis effectively generates rapid structural concepts for ideation. However, rigorous translation through a model-based systems engineering flow provides the actual actionability required for production. Every object in the final model must explicitly state its point of origin and its precise physical function. Most importantly, the model must isolate exactly what missing data a human engineer must approve before release. This technical schematic illustrates the final result: a fully governed system model where every physical part and abstract requirement pulses in a synchronized network. Through this translation layer, the synthesized drone becomes a traceable, mathematically sound engineering baseline.